Unit Operation Classroom. Today we are going to discuss the flooding velocity comparison for structured packings. That means we're going to compare the flooding characteristics of two different structured packings, P and Q. Let's read the problem. The flooding velocity, we'll see what flooding velocity is. Flooding velocity curves of two different structured packing. We'll try to have a schematic diagram of what is a structured packing as shown in this figure. So this is the figure which is given. The ratio of the mass velocities of the liquid and the gas are given. So basically, gx over gy is equal to 1.27. We'll see what is really meant by mass velocity. The density of the liquid and the gas are also given. Okay. For both the packings, the allowable superficial velocity, will see what is the allowable superficial velocity, and that is 60% of the flooding velocity. We'll try to have an idea what is the flooding velocity, and then we have to find out the ratio of the allowable mass velocity of the two packings, P and Q. So we'll try to have an idea about what is the mass velocity. Okay. So allowable mass velocity, first we have to find out the flooding characteristics and then we'll calculate what is the allowable mass velocity. Before we discuss this particular figure here, we will, let's look at the column. So this is a countercurrent packed column, and here the liquid enters from the top. Okay. And there is a liquid distributor here, which ensures uniform liquid distribution over the packing. So the liquid just falls on this packing, and there's a gas comes in from the bottom here. Gas enters below the packing and flows upward to the void spaces. And of course, as you can see, the gas and the liquid flow in opposite direction. Okay. Uh, the liquid mass velocity is denoted by Gx, and the gas mass velocity is denoted by Gy, and the units, of course, is kg per second of the gas. That is the mass flow of the gas divided by the cross section area of the column. We'll look into it. Of course, the liquid comes out from the bottom, and the gas goes up from the top. This could be a case of, might be like an absorption or stripping, etc. So here, of course, we're going to compare the performance of two different types of structured packings, P and Q. Any concepts used in solving the problem? First of all, flooding in countercurrent packed columns and the concept of allowable operating velocity. What is meant by that? Use of flooding velocity correlation, that means the graph, use of gas liquid loading and the fluid density parameters, X and Y. We'll look into it. Relationship between vapor mass velocity and the superficial velocity. We'll go into that. And the performance comparison of different types of structured packings for the same liquid and gas flow. What is superficial velocity? This is the volumetric flow rate of a fluid divided by, so it could be the gas or the liquid, divided by the total internal cross section area of the empty column. So let's say this is the let's say for this, for the gas here, what we see here. So for the gas, this is going in. Okay. So what we do here, this UO, that is the superficial gas velocity. This could be for the liquid also, is given in meter per second. This is called superficial gas velocity or liquid velocity. This is for the volumetric flow rate of the fluid. This is given in meter cube per second. That means meter cube per second of this gas, let's say, is going in. And that is divided by A, which is, of course, pi d square 4, that the total internal cross-section area of the packed column, calculated as if the packings are not there. As you can see, the unit of superficial velocity is, of course, meter per second. Now, what is mass velocity? This is the mass flow rate per unit cross-section area of the column. So this is the mass flow rate here, that is kg per second divided by the meter square, that means pi d square 4 of the column. That is the mass velocity. So mass velocity unit would be always kg per second meter square. Okay. So, what is the relationship between the mass velocity and the superficial velocity? Mass velocity, of course, is flow rate, mass flow rate divided by the area of the column. The mass flow rate, of course, is the density times the volumetric flow rate divided by the area of the column. Now, this, of course, is the superficial velocity. So, the mass velocity is equal to density multiplied by the superficial velocity. Okay, so we're going to use this equation in our calculation. We calculate the x here, which is of course we here let's given. So this is my x here. We calculate this one. So values of gx and gy, rho y and rho x, etc. given. So calculating the value of x is very straightforward. Uh, this comes out equal to 0.040. Okay. So now we read from the graph here the value of the ordinate here 0.04. This is my x. So this is a logarithmic scale. So this is 0.01, 0.02, 0.03, and 0.04. And for the corresponding 0.04, the value of y is 0.08, and the value for the packing p is 0.12. Approximately, this is read from the graph. Okay. So once we do that, so we can see the value of y, the ratio of the two y's, of course, is a ratio of this for P and the ratio of this for Q. And this, the densities, of course, remain the same because the gas and the liquid remain the same. So it's just a ratio of the flooding velocity. Flooding velocity for packing P and superficial flooding velocity for Q. So which is equal to 3 over 2. So the ratio of the flooding velocities for packings P and Q respectively, where UOF, of course, is the flooding velocity. So this the ratio of the flooding velocity is just 1.5 between P and Q. So this is the important one which we are going to use. Um, Now we have to find out if we go to the problem here, we found out the ratio of the flooding velocity for both the packings. The allowable superficial vapor velocity is 60% of the flooding velocity. So what really means? It means that, say, as we increase the what is flooding velocity, what happens if we keep on increasing the gas flow rate? So it impedes or prevents the liquid to flow. So at a certain point of time of increasing the mass velocity of the gas, of course, there will be a flooding. And of course, there's a significant increase in pressure drop, and the performance of the packing column drops very significantly. So it has to be avoided. So normally these columns are operated at 60% of the flooding velocity. So now we have found out what is the value of the ratio of the flooding velocities for packing P and Q. So it is saying that actual operating velocity, superficial velocity, is 60% of the flooding velocity. Mass velocity is, of course, the mass velocity is the superficial velocity multiplied by the density. Okay, since allowable superficial vapor velocity is 60% of the flooding velocity. This is given. Okay, so if we multiply it by rho I on both sides, we can say allowable mass velocity is, of course, given by this equation right here. This is, of course, the superficial velocity multiplied by rho y, and this is a 60%, 0.60 constant factor 60%. So allowable mass velocity would be equal to 60% of, as you can see, the flooding velocity multiplied by the density. Okay, so if that is so for P and Q, so this is the ratio here. So these two dy cancel out, this cancels out. So we get this basically allowable mass velocities for P and Q is equal to the ratio of the superficial flooding velocity for P and Q, which is equal to 1.5. So this ratio of the allowable vapor mass velocity in packing P and Q, that Q is equal to 1.5. That is the answer. So what are the key engineering lessons here? Number one, of course, the allowable mass velocity is 1.5 times, of course, the allowable mass velocity for the packing Q. That means, what does it mean? That means packing P permits 50% higher allowable mass flux than this mass velocity is a lot of times called mass flux. So mass flux than packing Q when both operate at 60% of their respective flooding velocity. What is number two? Pets with structured packings are quite often used in the industry, as for example, let's say carbon dioxide or H2S absorption from natural gas using amine solutions such as AMA, monoethylamine, diethylamine, distillation columns in petroleum refineries, gas scrubbers used for removing pollutants, like say sulfur dioxide, hydrochloric acid, or ammonia, steam stripping, deodorization columns used in various chemical and pharmaceutical and food processing plants. Chemical engineers must decide the safe vapor throughput in packed columns as if GY becomes too high, which I have already discussed, that means that the mass velocity becomes too high, the upward flowing gas impedes downward liquid flow, eventually causing flooding. Flooding is accompanied by increase in pressure drop, increased liquid holdup, entrainment, and unstable operation. So, of course, we do not operate the column at the flooding condition. So, we operate at 60% of the flooding velocity. So, the answer to this problem here is, of course, equal to 1.5.